The current automation practice is to produce one-of-a-kind, custom-built installations where the system cannot be easily modified to meet changing demands or adapted to advancements in technology. We need to design robot systems that are modular, portable, and easily reconfigurable to rapidly meet changes in technology or production requirements. Under the sponsorship of the U.S. Air Force Robotics and Automation Center of Excellence, RACE, Advanced Cybernetics Group is developing tools for building robot systems quickly and cost-effectively. The tools include a library of standard software modules. Each module has a defined plug-and-play interface to allow them to be easily replaced, to be modified, and to take into account advancements in technology or changes in production requirements. The modules have been successfully employed by us and automation system integrators to rapidly generate robust robot systems.
The United States Air Force has a requirement to perform periodic maintenance on a large range of weapon systems. In order to meet those requirements, in an era of shrinking budgets and increasing internal and external competition, remanufacturing processes must be upgraded. Unfortunately, most of our depot remanufacturing processes are not suitable to classic robotic and automation solutions. I'll take a couple seconds now to talk to you about the different constraints that majorly make that happen. First of all, we deal in small batch sizes. We don't have thousands of cars or millions of widgets. We have tens of planes to work on a particular year in a depot process. We have a lot of feature uncertainty, both in the placement of where the part or workpiece, in this case the plane, is going to be when we work on it, and what we're going to be working on in the plane itself. We don't have CAD models to help us with that. We're going to have to do this in an era of having our existing workforce still in place, and I want to do it with high reliability and maintainability. Custom solutions in the past didn't work. You got to be able to call up and get a response and get something fixed. And all of this has to be done with low insertion costs. The Air Force Materiel Command Robotics and Automation Center of Excellence at Kelly Air Force Base in San Antonio, Texas, developed a Unified Telerobotic Architecture Program, or UTAP. Under the aegis of UTAP, the Advanced Cybernetics Group, ACG, was contracted to validate our fundamental thesis, which is that existing commercial systems could be cost-effectively extended to meet our existing telerobotics requirements and provide a base for future evolution. A common set of core telerobotics capabilities, a telerobotics toolkit, if you will, emerges. At the top of that list is the ability to fly above a surface. In more technical terms, autonomous regulation of separation or standoff distance in the direction perpendicular to a work surface, while the operator controls the motion parallel to the surface, maybe with a joystick, maybe not. Second is the ability to follow the surface. Again, in techno-speak, autonomous regulation of force in the direction perpendicular to the work surface, while the operator controls motion parallel to the surface. That'll allow you to move along and do some surface finishing. Visual registration of the workpiece, quite simply, I have to know where it is I want to be able to work on. Maintaining angle of attack. A lot of times the tool has to be held at a certain angle. I got to maintain that angle between the tool and the workpiece. Autonomous regulation of angle between the tooling axis and the workpiece normal. Again, while the operator controls the trajectory. Finally, the ability to learn a workpiece dimensions by visual-based tracking of a workpiece trajectory. I might want to just go out and mark the area that I want to cut out with a black grease pencil. I want to be able to follow that with a vision system that will memorize that locations of that part and be able to bring it back in and be able to work on it later. For the purposes of our demo, we just did those in a planar system. The ACG efforts you have witnessed in this tape have not been done in a vacuum. In fact, these efforts are connected to a larger overall UTAP program. What you've witnessed is the output of a Phase 2 demonstration phase, the purpose of which was to initially validate the JPL NIST UTAP architecture. That architecture has been under development for about the last year and a half and is closely linked to other JPL and NIST architecture efforts, such as the Enhanced Machine Controller, or EMC project. It's also linked with other national efforts, such as that sponsored by the National Center for Manufacturing Sciences, NCMS. They are currently running the NGC program, and under that umbrella, our telerobotics architecture can be looked at as an application architecture.
In my many years of experience in the field of robotics, I've seen numerous demonstrations and countless papers on the subject of general-purpose robotic automation. Few of these embryonic thoughts and examples filter down to solid factory or hangar floor applications because of a myriad of reasons, mostly relating to the failure to effectively deal with all of the real-world applications issues. The unified telerobotic approach and the telerobotics toolkit technology will close the gap between demonstrations of concept and practice. In fact, we already have some concrete examples of practical applications. At Warner Robins Air Logistics Center, robotic CO2 paint stripping has been tested on F-15s using surface sensing and motion planning tools. At IBM, hard disk platters are rapidly and accurately loaded into sputtering fixtures using sensing, measuring, and surface mapping tools from the toolbox.
IBM and ACG jointly developed the software system for multiple loads of disk drive platters into the ULVAC sputtering machine. IBM required the system to be agile. That is, the software has to be written so that it can be inexpensively and rapidly reconfigured for different disk sizes and pallet geometries. The software was initially developed for the 65mm disk line. The initial changeover to 95mm disks was accomplished in 2 days.
At the Schlaglock division of Ingersoll Rand Corporation, rough cast door levers are being sanded and polished with a robotic system using force sensing and surface contouring tools developed as part of this program. The UTAP is an excellent example of how government and industry can cooperate to produce key enabling technologies that will provide immediate utility value to the government and return the United States robotics industry to world-class prominence.
The United States Air Force contracted ACG to develop active force control technology required for demanding applications in precision assembly and surface finishing. Software developed by ACG is being applied here to follow a contour based on force data supplied by the blue force sensor mounted at the robot wrist. The data is being used to modify robot motion in order to maintain a constant contact force on a changing surface. Real-time motion control is especially useful in situations where multiple sensors are involved. In this demonstration, we are moving the robot under mouse control and sampling force data at the same time. Notice that the robot reacts to the hand by backing off. The resultant behavior is thus safe. This feature is useful in advanced telerobotic applications.